All right, good. So apparently I should be ready by now. So I'm Peter Starr. I'm from Thomas Schulte's group. I think some people might know our group by now. So I'll be talking about like what I've been doing over the course of my PhD, and basically how we ported DCA Plus to GPUs, because really if we talk about PITSDYNE, the real innovation is the fact that we have this this hybrid supercomputer which has extremely good performance. It's number 6 in the world. Now, the DCA Plus was basically conceived as a program to compute the phase diagram for the high TC superconductor. So I'll give you like a short introduction to what this field is. Of course, I will not go into the details of the physics, but just to give you an idea as to why are we doing DCA Plus. Now, really during my PhD, we did. When I was discussing with Thomas, we really had this idea of trying to attack getting the phase diagram of the cuprates in a threefold way. So we wanted both doing algorithmic changes, algorithmic improvements. We wanted to push these algorithmic improvements to the GPU, and we actually tried to make the algorithmic improvements in such a way that the GPU would profit from that. And on top of that, we wanted also to use very large supercomputers such as Titan, but of course also PITSDYNE. So these three parts of it, scaling, new algorithms, and new architectures, were really the three components. And really what I want to focus on today is just to look at the algorithm and how this connects with the new architectures such as GPUs, which is, of course, relevant for PITSDYNE too. So quick history of superconductivity. So in 1986, there was this big revolution. So on my birth year, basically, they found this lanthanum copper oxide, and then afterwards they found some other superconductors. And although there was already a theory about how superconductivity arose, basically this didn't match at all. So the theory basically said, okay, you can only have a TC up to 40 Kelvin, and all of a sudden they found materials up to 140 Kelvin, which clearly did not match. And so they soon found out the crystal structure, that the superconductivity essentially arises in these 2D layers in the material. And a year later, somebody came already up with the model and said, okay, actually the essential physics should be captured by this single band Hubbard model. But then, ever since then, since 1987, basically nobody came up with a correct phase diagram, in the sense that everybody can qualitatively draw it, but nobody can put numbers on the x and the y axis. And so the goal of the DCA is actually to put numbers on the x and the y axis. So what is a TC now for what type of doping? Okay. So the way it does that is, it's the dynamical cluster approximation, or DCA. That is the name of the algorithm. Effectively, what it does is it tries to find a complex function, which is called the self-energy, which entails all the lifetime of the particles and so on and so forth. And the way it does that is by solving a finite-sized system embedded into a mean field. And you find that mean field effectively in a self-consistent loop procedure. So you start with the guess for the self-energy, then you map the whole lattice onto a finite cluster embedded in that mean field, and that you do with a simple coarse-grained procedure, which is an integral, again, embarrassingly parallel to implement. Afterwards, you solve the cluster with a quantum Monte Carlo, which is, again, very easy to implement because it's embarrassingly parallel. And then after you solve the cluster, you basically do a lattice mapping where we try to infer the mean field of the lattice by a consecutive interpolation and deconvolution. And what it essentially does is, if you do this properly, then you see that you get actually numbers on the x and the y axis. And furthermore, if you look at the phase diagram, it actually looks very much as to what people have been drawing in science and nature papers for a long time. Also, you can look at symmetries, and basically you can see that for the superconductivity, you see a nice D wave. So that's great. Now, what isn't so great with the dynamic cluster approximation is, first of all, you can't really do big clusters. So for a U over T, this is a parameter range, U over T equals 7, which is thought of as relevant for the cuprates. You see that the DCA basically can only do 3 clusters, and there is such a big difference between the TCs that you can't really infer the correct temperature. And even for U over T, even 4, so the interaction is a bit less strong, and so it makes it's actually easier to calculate. We still have these large fluctuations. So for each of these different type of finite-sized clusters, you get actually very large differences in DC, and so you can't really infer what the transition temperature is in the lattice. And so basically what we wanted to do was to find a new algorithm, DCA+, such that we can push to much larger clusters and also to actually get rid of this large cluster shape dependence. Now, I will not talk about the details about the cluster shape dependence because that's really physics. But I will be talking how we can try to push, to go to larger clusters because that's clearly also a big part of what we need to do. Okay, so effectively speaking, as I said, like 99% of the time you spend in the DCA is really spent in the cluster solver. So this whole loop, this little box, this is where all the magic happens. And so once you write this out, this is actually a fairly non-trivial operation. But, yeah, okay. So, and as with any cluster solver, as with any quantum Monte Carlo solver, you effectively always have two sides to it. One, you have to basically sample the partition function. And in our case, what this basically comes down to is calculating determinants of matrices. And these matrices are basically generated stepwise. So we take a bunch of spins, and then we need to start flipping the spins. And for every single time that we flip a spin, we need to take the old matrix, do a vector outer product on it. We get a new matrix, and then we need to compute a determinant. So the problem is doing this vector outer product is, of course, memory bound, and so it's extremely bad, both on CPU and GPU. So we need to get rid of that. Then the second part is we don't only have to go through the configuration space, but we also have to measure from time to time observables. And these, in our case, what this comes down to is actually non-equidistant Fourier transforms. Now, Fourier transforms themselves are already a bit bad, but non-equidistant Fourier transforms where the time points are, well, non-equidistant. This you can, in a naive implementation, is a matrix vector multiplication. Is again again memory bound, and so again extremely slow. So before we go into like how we change the algorithms to actually map on the better hardware, so just to give you an idea, if you start with Titan or Pitstein, effectively if you do a quantum Monte Carlo, you basically do the embarrassingly parallel thing. So you give a bunch of nodes exactly the same task, but with a different random number generator. They do a walk. And effectively, on each of these nodes, you will have now two things you have to consider, especially if you do a hybrid. One, you want to have new algorithms, right, that basically will shrink the time. And the other thing you have to think about is actually how do we rethink the node parallelization. So in both cases, as we will see later on, you will have to kind of optimize, and you will get actually very nice speed-ups if you attack both at the same time. Now, of course, I think in this thing we have already seen what a GPU is and what a CPU is in the sense for the specification. But just to clarify, so effectively, if you look at the GPU from Pitstein to Titan, you see that you have 14 SMXs, which is kind of like a core. They run at a much lower speed than the CPUs, typically 730 megahertz, and they have much, much less cache. But they have a lot more threads per core, and they can do a concurrent copy and execution. While in Intel Xeon, basically what you have there is a bunch of few threads, say 16 threads, but they run at a much higher frequency, and also they have much more cache. And they can't do a concurrent copy and execution. And so what it turns out to be is that whenever you have very large data sets, the GPU is very good at it. It can do doing number crunching. But whenever you have actually very small data sets, typically the CPU wins out. And so this is what you effectively see is that when you look at the papers that they're written on this, and this is even given by Intel, right, that normally, typically, you get on very large data sets, you get around 2.5 times speed up with the GPU. And if you look at the NVIDIA propaganda, then effectively what you see is that whenever they say, okay, how much more we speed up, it always is in such a way that the data sets are much, much larger than the cache, so that, if it doesn't fit into the cache, the GPU will win. That's basically, the way you have to read these things. Okay, so now let's get going back to the special, the DCA+. So again, I will look at these two, sampling and the measuring. Okay, so what the idea here was actually to use the idea that people have been using for a long time in the LU decomposition is to see, okay, we do a spin flip, we do a spin flip, we do a spin flip every single time we do a vector outer product. Now the question is, can you actually compactify this into one operation and basically do like a kind of a matrix multiplication of a fat vector with a fat column with a fat vector. And indeed, yes, you can do this. If you look at the way the LU decomposition happens, is you start with a partially decomposed matrix, then you take a small matrix that fits into the cache, you do an LU decomposition, then you update the panels, which are these red things here, and then once you have updated the panels, you get a matrix that is again partially LU decomposed, but which is of course grown now. And so the idea was actually to recognize that you have this vector outer product here and this vector outer product there. And once you make that connection, you can actually rewrite the algorithm such that you increase data locality. Because really that's basically the only thing you do. Instead of doing KS of these vector outer products, you now do in one step a matrix vector multiplication where this is now a size of KS. And so in this way, effectively, instead of doing just a memory-bound operation, you now do a compute-bound operation. And if you now vary the KS, this width of this vector, if you increase that, you see that the number of updates you do per second basically goes down. And this is for different sizes of the matrix. So this goes down, and at some point, it obviously saturates, because at that point, you've used the maximum or you come at the performance, the optimal performance of the matrix multiplication. And so now the reason why I think this is actually quite nice is what effectively happens is the following. So you have this tiny matrix, which basically perfectly fits into the cache. So that one, you can make up to 120 to 256, and then at that point, you run out of cache. So, and this is also what you see here. So here we can go up to 256, and then we're basically done. And this, of course, this LU decomposition of a small matrix that fits into the cache is extremely fast. And then afterwards, what we do is we try to push the large matrix multiplications that don't fit into the cache. We push that to the GPU, and we get actually very good performance. OK. So that was kind of the sampling. Let me think also a bit about the measurements. So here it's actually even more interesting. So here you have, for this non-equidistant Fourier transform, you basically do this matrix vector multiplication. And here you can actually rewrite that this formula you can rewrite by using a convolution. So what you effectively do is you use the convolution theorem, right? So if you do a Fourier transform over non-equidistant function values, what you can do is you can convolute each of these function values with a kernel phi, which is very, very localized. And by doing this convolution on an equidistant mesh, the data itself is, again, very local, and so the CPU is very happy. And so once you've convoluted on an equidistant mesh, you can do a fast Fourier transform, and then afterwards you still have to renormalize this by the Fourier transform of the kernel. But and on top of that, since we're actually always accumulating, so we have this plus equal, right? And the fast Fourier transform is a linear operation. Effectively, you can push that fast Fourier transform all the way to the back of your accumulation or your integration. And so what effectively this means is that instead of doing every single time for the matrix for the accumulation a matrix vector multiplication that is n square in operations, you now do just a simple convolution with a very localized kernel, and so you replace this n square with a complexity of simply n. And that means that if you have, for example, 512 frequencies, which you typically have, then of course you get around that type of speed up, and you see that the speed up here is around 500 to 1,000. So the order of magnitude is by just simply rewriting this with the math, then using the CPU with the fact that we have very localized operations and that can be performed very efficiently in the cache, we get actually a speed up of a factor of 1,000, roughly speaking. Okay, so far I've basically been talking about like shrinking the time, so improving the algorithms such that the time to do something is reduced significantly. And this was with the submatrix update algorithm and the NFFT. And so now the question is, can we even push this further? So can we actually get extra speed up by rethinking the node parallelization? And it turns out that is yes. So what you do here is the following. So typically, and this is actually a very interesting exercise, by actually forcing ourselves on this hybrid multi-core, we had to rethink the node parallelization. Normally, if you have a CPU and you do like a quantum Monte Carlo integration, effectively what happens is you just put an MPI task on each core, and then you let the MPI task do a bit of the configuration sampling, and then a bit of the measurement, and then configuration sampling. So effectively, you consecutively do sampling to the configuration, measuring, sampling to the configuration. Now, that obviously doesn't really work anymore on the GPU because you can't just put an MPI task on the GPU. It has to be directed by a CPU. So what we did is we basically decoupled in our integrator the walker and the accumulator. And we said, okay, well, let's just throw out a bunch of walkers, a bunch of accumulators, and let them talk to each other. And whenever a walker has a new configuration set, he will find the first accumulator and then dump his configuration into this accumulator, and then the accumulator takes care to actually accumulate or to do the measurement. And so that basically allows us to use two technologies that the NVIDIA provides. So one, it allows us to use the streaming. So what we now want to do is we want to do all these matrix multiplications from the walker on the GPU. So whenever a walker updates a small matrix, he pushes that to the GPU. Then they do a matrix multiplication. And after the matrix multiplication is done, he downloads a tiny matrix again to the CPU, does again an LU decomposition, and so on and so forth. And at the same time, whenever then the walker is finished, then he can say, okay, we start and we push now this configuration to the accumulator. And so essentially what happens here is you have a lot of accumulators that are working on the CPU whenever they get a new configuration, and all the work for all the matrix multiplications are now shifted to the GPU. And so instead of having this picture where in the green we do the walking, and in the orange we do the accumulation, we now have pushed all the green to the GPU, and since we know that the walking is essentially a matrix multiplication, and that basically runs much faster on the GPU, all these matrix multiplication are compressed significantly, and so we get much more or measurements done per time. And that's basically what I want to show here. So here I was running on an XE6, so basically on Rosa, and so what I was also playing around with was, okay, so I want to get the maximum performance, but I can also now start playing with the ratio of the number of walkers versus the number of accumulators. So what you see here is on an XE6 with two CPUs, I started to say, okay, what about, let's measure the performance if I have 7 walkers to 1 walker, and of course, the number of accumulators is just 8 minus the number of walkers. And what it turns out is that we get actually the maximum performance at around 6 to 7 walkers. That means that on my CPU system, all of them want to go through configuration space, and my walkers are so slow that I can get around with just 1 accumulator. That is because he has to wait all the time for a walker to generate a new configuration. If you do this on a GPU system, so we start again playing around with the ratio, what happens there is that you see that the maximum performance is basically 2 to 3 walkers. So really, all my processes want to be accumulators because my walkers on the GPU are so fast that they can supply so many configurations that I need much more accumulators than walkers. And so just by playing around with to actually find the best performance on CPU, or on CPU, GPU, you see that you get a totally different system. I mean, a totally different dynamics. And also, we get, of course, a much higher performance with the GPUs, around 700 to 800 gigaflops per node. Okay, so then we did also some tests of time to solution and energy to solution, where I should say that Gilles helped me a lot. So here, so if we just look at saying how many measurements can I do effectively per node in the most optimal case, if I take the most optimal configuration in terms of the ratio of walkers per accumulators, then we see that effectively we get a speed up. So the red curve is essentially the speed up of 1 CPU and 1 K20X versus 2 CPUs, and this speed up is around 6. Of course, this also correlates to the energy to solution. So if we, instead of just saying we measure the time per measurement that it takes on each of these systems, we look at the energy to solution, and we see that we get even slightly better. So it's a little bit more than on average, 6, I would say. It's around 7. And so, of course, this translates to if you can go much faster, and even if you use much less energy to solution, then that actually, especially with Titan, this translates to a lot of money. Okay, then I have another slide which I find actually quite interesting. So if I now look at the typical matrix sizes which I look at, and I look at how many times or how much did I actually speed this up compared to the original, let's say, naive implementation, what you see is you get actually a very nice speed up for the small matrices, and the reason there is because we've translated this from memory bound to compute bound, and the nice thing about this is that here the matrices more or less still fit into the cache. So here, with small matrices, everything fits into the cache, and the CPU is of course very happy, so it can perform a lot of calculations. And then here, once you go actually to large matrices, then you see that the speed up again starts to pick up, and this is because the GPU, the bigger the matrix, the more the GPU is happy, the more performance I get, and so the better, the more speed up I get. So small matrices is extremely good. Very large matrices, I get also extremely good speed up. If you go somewhere in between, which is like, say, the size of 1,000 or 800 to 1,000, there you see that the speed up is a bit, well, it's still a factor 30, but it's not so high, and the reason is because you cannot really use the cache, and also it's still too small for the GPU. And so there is an interesting dynamic that goes around there. Yeah. This is as a reference. So what I did was I took both. So I started with the simplest implementation where we don't have any threading whatsoever. You just have the simple, every MPI task per core. And then what I did was, indeed, I ran on the CPU, either CPU version or the GPU version. So here, basically, this would go down like that. If I don't use the GPU, basically, and this would be if I do use the GPU. So so this basically crosses over effectively, and the maximum performance is sometimes you have to use a GPU and sometimes you don't, and here is probably the crossing point where the GPU starts taking off. So, but this was actually in the beginning very frustrating because I was doing small tests on 30 all the time, and I was seeing that the GPU didn't really help me at all. I was very frustrated. The CPU version beat the GPU version all the time. But I was doing this for around 500. So I didn't realize that that was actually bad until I saw what the performance was for cuBLAS on around 500. And then I started pushing this because at the end of the day, we want to go into this region because this is where actually the TC or what transition happens. But for small test cases, you generally don't want to do that because it takes a longer time. And so this is kind of like a composite figure of both cases where you look, do I run everything on the CPU or do I run everything on the GPU, basically? So that was, yeah, you have to be kind of careful to not stick to one testing case because then it turns out that you look at the wrong things. Okay, then quickly on the scaling and performance because I did talk about that a bit. So this is, of course, a plot that comes from the Gordon Bell paper. Well, there's not, we see, because we actually improved all these algorithms very much and we got so much speed up and so on and so forth, our thermalization time compared to the old code dropped significantly, which means that the serial part, the thermalization part is actually the serial part of your, is equivalent to the serial part of our algorithm. Since that dropped dramatically, we got a much better scaling, and so we could more or less linearly scale to 20,000 nodes. It's not exact, it's not perfect. You see that here it's not completely on the line, but I think it's good enough. And we got something like, the most I got was 15.4 petaflop. On this plot, it was still 13.9. Okay, then I come quietly to the end of my talk. So, as I said, I've talked a lot about algorithms and the GPUs and how basically how this connection works together to get you the best best performance and also the best science. And so at the end of the day, we actually could get a converged DC, which made Thomas very happy. But of course, all these things hang together. So if I wouldn't have had this large computer and I wouldn't have had a perfect scaling, then of course this thing would have been nice, but it would really have helped very much. And it works in all the cases. So if I wouldn't have had the GPUs, it would have been a lot harder because again, the GPUs did actually allow me to scale to very, very large number of nodes. And of course, the algorithm was absolutely essential to get anywhere with our results. All right, so I think I'm getting to the end of my talk here. Yeah. Sure, accumulators, yeah. You can do it dynamic, basically. But what I do here is so for example, what we do typically is just we run the same test, which we think is representative of what we want to do in our physics papers, whatever, and we just do this for a bunch of configurations. So I typically the number of threads is typically fixed. So on PITS-9 it's 16. So then I run basically one accumulator, two accumulators, and for one accumulator I have 14. I do 14. Say again? No. You don't have to No. These are all dynamic variables. I mean, I have been told that maybe we should even dynamically start pushing, adding more walkers or deleting them depending on but this seems to be very complicated. So right now it's just in the input file you just say, okay, I want to have so many walkers, so many accumulators, start running basically. Yeah. Because at the end, it's a very fixed number. So I just need to run these things once on a machine, and then that's it, basically. Yeah,